start with the webinar.
I think this sounds okay. We will start from here. I will introduce about IIW very briefly, as we have been promoting IIW. Then I'll not take much of a time to inform all the audience about the international conference in 2024, a short information on that. And I believe SigmaWeld, we will give them 2 minutes to speak, and then we will hand over the session to you. And yes, as you briefed, you can run the video, you can introduce Gary, and you can directly hand over it to Gary for his session.
Great. Sounds good to me. Yep, absolutely.
Yeah. Good.
If you want to just bring the host back to me, I'll share the screen initially, and we'll just make sure that it works. So.
You want to try to share, Gary, or we will do that once you are on?
Well, he went back. I need to be made host. I don't know if that.
Okay, I will make you the host.
No, they always have to give you permission. Yes, I as well at the moment don't have permission.
Yeah.
Our office, our Sachin will give you the host access. Yeah.
Yes, correct.
Sachin, can you hear us?
Yeah, you are a host now. Gary, so you are host now.
Gary, he has shared the host access to you.
Yeah.
Just check.
Yeah. Now that's why I'm a little. I'm just trying to see. Oh, I see. Right. Yeah. No, I just. It's always we use Teams a lot, and So you can see it now. Yeah.
Yes.
Absolutely.
The screen is visible.
Yes.
Yeah. Okay. And
nice. Do you have a video, Gary?
No.
No. Okay. Good.
Okay.
So I'm going to stop sharing.
Hello, Abhishek. Hello, Abhishek.
Yes, Sachin. Yes, tell me.
SigmaWeld will present for 2-3 minutes, sir.
Yeah. I have spoken to Nimesh Bhai.
No, Sanjay is there. Sanjay Yadav is there.
Yeah.
Hello, sir. Am I audible?
So yes, you are audible, Sanjay.
Yeah.
So Sanjay, what we will do is I'll start briefing about IIW, then IC 2024.
Okay.
Then I will give you the slot for your talk, 2-3 minutes, and then we hand over it to Gary and his team. Okay.
Okay. Thank you.
Okay.
Hello.
Yes, Sachin.
Start Abhishek, no introduction. Mumbai brand. Sanjay. Hello, Sanjay.
Yes. So Mr. Abhishek will present now. Introduction.
Yeah.
Yes. Okay.
Sachin, I think we should start.
Yeah, introduction you can start now.
Yes.
So I'll start introduction with ourselves, IIW. Okay.
Yeah.
I'll share my screen. Okay, that has been. Can you give me the screen share access, Sachin?
So I will give the same for access to you. Just postpone. Abhishek, now you are the host.
Okay,
Abhishek, you are host now. After completion,
okay,
hand over to Sanjay. Okay, I'm just
okay, okay. Just give me a minute. I hope you can see the screen, Sachin.
yes, we can see you.
The slideshow mode.
Yeah.
Okay, so yeah, a warm good evening to all of you, all the participants and everyone joining us today for this webinar, Weld Tech Talk. I am Abhishek Vyas. I am representing as the Honorary Secretary of the IIW Mumbai branch. I will just take you a little bit about the Indian Institute of Welding as a whole and what about the Mumbai branch activities. So as you may be attending this series of Weld Tech Talk series, it's the part of IIW Mumbai branch, whereas IIW Mumbai branch is an affiliated branch to the Indian Institute of Welding, which was found at Kolkata, incorporated in Kolkata in the year 1966, having 4,500 plus member strength, and is a member society to the International Institute of Welding. The major objectives of we at IIW is to assist human resource development in welding, technology diffusion, technology sharing with regards to industry knowledge, know-how about the welding, foster research and development in the welding sector, promote health and safety in the welding, and establishing international standards of quality for the Indian fabrication industry. We do conduct a lot of activities like conducting technical meetings, workshops, various training programs. Like one of these is what you are attending, webinars, conferences, international conferences. One of those conferences, I'll brief you very shortly about after the slides. We also have Indian Welding Journal publication, which gets published every quarter in collaboration with AWS. And you can find out all those details on our website as well. We also foster we also cater the welding and training certifications like IWE, IWT, IWS, and so on and so forth. We also promote the skill council. We work with them for the skill development of welders. Yeah, we do also conduct the National Welder Training Certificates and the competitions for them. We also help manufacturers, industries with the certification scheme as per the requirements of ISO 3834. Also train the trainers, industrial visits, welder competition for male and female both, and many more. These are the various benefits of becoming an individual member of IIW. Like you can take advantage of several courses and examinations at a discounted rate. You can acquire and disseminate welding knowledge. You can get a platform wherein you can show your expertise as well. You can get free access to various quarterly published journals, monthly technical lectures of various branches where you are getting connected with, and many more benefits like this you can access when you are an IIW member. These are the details which is also available with our office bearer. In case you need any information, you can get in touch with Sachin Surve or any of us. If you wish to become an industrial corporate member or individual member, these are the charges. I'm not discussing about them in details right now. I'm just showing the slides to you all. Yeah. This is Mr. Sachin Surves, the office bearer for Mumbai branch. You can reach out to us on iiwmum01@gmail.com. I will just take you a little quickly through the IC 2024 event, that is the 6th International Congress organized in the month of, going to be held in January 2024, between 22 to 24 January. So basically, the theme of this is advancement through sustainable and green welding. And it will also have Weld Expo, the exhibition for welding, cutting and joining. And it will be held in Bangalore International Exhibition Center. In addition with the IMTEX. IMTEX, you may all be very much aware that is the biggest engineering expo as far as India is concerned. So it is in concurrence with that. So we would like to promote this event to all the participants who are listening to me right now, so that we can help you get participate in this IC 2024 event. So we can share, these are the details available on IIW website as well. I'm just scrolling to all of you. We are inviting all the authors to present their research work. Topics you can see like advanced manufacturing, welding and cutting processes, additive manufacturing, advancement in green welding, industry, industry 4.0, Internet of Things, and many more developments occurring across. So 31st October is the 15th October, you can see that is the deadline for receipt of various abstracts. These are the delegate fees. This is just for your reference. You can find out all these details on our website. If you wish to sponsor, there are certain details also available. And yeah, these are the committee members for that. We would also like you to brief about the Weld Expo, which is also going to held between 19 to 23 January, along with IMTEX. So as you can see here, it's in Bangalore. So both these events are going to get run at the same time. 22 to 24, the conference will be there, and 19 to 23, there will be this exciting welding expo going to be held in Bangalore in the month of January 2024. So if you wish to have any or more details regarding this, you can reach out to us. And now I would like to hand over to SigmaWeld for their corporate talk. Sanjay, are you there?
Yes, Abhishek. Yeah, yes, Abhishek.
Give me a minute. I'll try to give you the host access. Just give me a minute. Sanjay, can you have the screen sharing access?
Yes. Yes, I have. Okay.
Yeah.
Good evening and warm welcome to all the participants in the episode 28 of Weld Tech Talk. Today we have a very interesting topic of how can I know if my stainless steel weld is sufficiently corrosion resistant, which would be covered by Mr. Gary Coates, Technical Manager for the Nickel Institute. As the topic is about stainless steel, we have helped our clients increase their productivity in TIG welding for approximately 10 times from their manual process with our SWOT technique. And this SWOT technique we are demonstrating next week in an exhibition in Greater Noida, the Stainless Steel Expo. So just sharing a screen. Requesting all of you who have interest in stainless steel welding, please do visit. Also a small video of our company presentation. Thank you, Mr. Abhishek. And
Yeah,
Mr.
thank you,
Sachin
Sanjay.
for giving the opportunity.
Thank you, Sanjay, for your the video details and all.
Yes.
Yeah, Jurg would like to take now the session. We would like to hand over it to you. Sachin, can you make him
Thank
the
you very
host
much.
now?
I will make the Gary host.
Very interesting. I will see Sigma at the exhibition next week. I will definitely come and see you at the booth.
Great.
I will be there as well.
Great, great.
So let's see if I can share my screen. Nope, still not possible.
Abhishek, you will have to make George the host for
Yeah, I
that.
think Sachin will do that. Sachin is anyways doing that.
Just a minute. I'm doing.
Yeah, yes,
Sure.
Sachin.
Good evening, George, and I'll be meeting you in Delhi maybe on 3rd at the show.
Let's do that. Absolutely.
It's been a long time.
Yes, that's true. So, okay, I have now the possibility to share the screen, sound and optimize as well. Okay, I hope you all can see now my screen.
Yes.
Yes.
Perfect. Okay, and with that, I would like to start with a good evening to all of you and a very special thank you as well to the IIW Mumbai branch for having us on today's webinar. My name is Jörg Schweitzer and I'm the Market Development Manager for Southeast Asia in the Nickel Institute. This webinar is also supported by the International Molybdenum Association, IMOA. I would appreciate if I'm allowed to quickly introduce the Nickel Institute and IMOA to you, and of course, afterwards, the speaker of the evening, Mr. Gary Coates.
Yeah.
So, as you all might be aware, nickel is a key element in over 70% of all stainless steel produced. It, of course, delivers outstanding physical as well as mechanical properties, and that's why stainless steel is such an attractive, easy to use, and long-lasting solution. We are a global non-profit organization of the leading primary nickel producers. Our mission is to promote and support the proper use of nickel in the appropriate application, and that's why we do as well these webinars. Our headquarters is in Toronto, Canada, where as well Gary lives. We have an office in Washington and Durham, South Carolina, the US. And there is actually our science and research center. The European Center of Excellence of the Nickel Institute sits in Brussels. And there are two more incorporated offices, one in China and one in Japan. Then we have two representative offices. One is located in Australia, the other one in Singapore, where I'm sitting. This is an overview of our members that actually fund our organization and at the end of the day, these events. So IMOA is like the Nickel Institute. It's a non-profit organization. It represents the majority of all the molybdenum industry globally, and it promotes as well the properties and sustainable benefits of molybdenum in all applications. Molybdenum is a key alloying element, and that provides improved corrosion resistance. Now a short video.
Nickel is a naturally occurring element. It's a metal. It has outstanding physical and chemical properties. And these properties make nickel inevitable in our daily life, notably in stainless steel, in pots and pans, in cutlery, in mobile phones, in computers. We see nickel playing an increasing role in emerging and future technologies, such as, for example, EV batteries, or in renewable power generation. Criticality usually assesses on the one side supply risk and on the other side the economic importance that a raw material plays. And that criticality assessment varies from region to region. What these assessments all have in common is that they identify a very high economic importance that nickel plays in emerging and future technologies, such as, for example, clean energy provision or in green mobility. And therefore we consider nickel to be a strategically important raw material with a high economic importance. When people talk about availability of nickel, they often use the terms resources and reserves. And it is important to understand what they mean. Resources describe potential future ore deposits where still exploration needs to be done. And on the other hand, we have reserves where exploration was already done and where we know that these ore deposits can be mined in an economically viable way. Today, there are 90 million tons of nickel reserves known, as well as 300 million tons of nickel resources. Companies are adding on a continuous basis new ore deposits to both the resource as well as to the reserves. At current production levels of 2.5 million tons per year, we can say that there is enough nickel for current and future generations. There are two main types of nickel ores. On the one side, sulfidic ores, and on the other side, lateritic ores. And they are converted into a wide range of different nickel products. There's a common misconception that only sulfidic ores are suitable for batteries, an increasingly important application of nickel. This is not true. Both ores can and are already converted into the nickel qualities suitable for batteries. Nickel is not consumed as oil or gas, it is used. Nickel can be infinitely recycled, and recycled nickel has the same properties as nickel coming from primary sources. 85% of all nickel that leaves the use phase is recycled. More than 80% of all nickel that historically was mined is still in use, meaning that it is available in future to help satisfy the growing demand. It takes a mining company more than a decade between exploration and the production of its first ton of nickel. For recyclers, also significant investments are required before they can start producing nickel from recycling. What both have in common is that they require a stable regulatory framework, which is providing them with long-term planning security, and this will allow nickel to play its critical role in the future.
Yeah, and with this, it gives me great pleasure to introduce today's speaker, Gary Coates, who most of you know already from previous webinars and events in India. Gary has worked in the stainless steel and nickel alloy industry for almost 50 years, and the last 25 with the Nickel Institute. Welding has always been a major interest of his, as often welding is the weakest link in fabrication. He worked in many different end-use industries and with fabricators to ensure that they have access to the proper welding informations. He is actively involved with many professional societies, including the American Welding Society, and is an active contributor to their welding forum. He has made many presentations around the world, and that on all aspects of use of stainless steel and nickel alloys. With this, it's my pleasure. I hand over to you, Gary, for the talk of the evening.
Okay, thank you, Jörg, and thank you also to the IIW Mumbai chapter. I always look forward to giving presentations there, and because we have such an audience that is interested in learning more. So let me see if I can share my screen.
Share the screen. Gary, sir, you're the host now. Gary, sir, you're the host now. You can share the screen. Please share your screen.
It's showing I cannot share the screen.
So you are the host now.
Maybe you can check again. It will take
I will
little
check.
time.
Yeah, it says host disabled
No,
participants
actually,
screen sharing.
host has
Oh.
been made to Graham by mistake, I guess.
Ram is, I will again. Just a
Please,
minute.
yeah, thank you.
I will do.
Thank you. Gary, you should be able to do now.
Yeah, thank you.
Yeah.
Thank you.
Okay. Can everybody see the screen now? Yes.
Yeah.
Maybe. Okay, great. So my talk today relates to whether you can know whether that stainless steel weld that you had just made is sufficiently corrosion resistant. So I have a short introduction. I'm going to talk about two major areas. We call them physical areas and metallurgical issues, and then a summary. And of course, one has to get into one's head the fact that most welders and even many welding engineers, they think that if they can pass a bend test and a tensile test, then their weld is fine. And that is largely true with carbon and alloy steels, but with stainless steels, corrosion resistance is very important. So stainless steels are used primarily for either their corrosion resistance or for high temperature, where strength at the high temperature and resistance to oxidation or carburization or sulfidation, etc., are required. So I'm only going to talk about aqueous corrosion resistance here and how it is affected by welding, both by improper welding techniques and even if normal proper techniques and procedures are followed. So I'm going to give you also tips on how to ensure weldments. And by weldments, I use that term to mean both the weld itself and the heat affected zone, and you want them to be equal to or better than the base material. So questions we want to ask: what stainless steel alloy should we be concerned about? What service conditions we could be concerned about, because we don't need to look at everything in terms of, well, everything is going to be bad in certain instances, and what actions we can take to ensure proper corrosion resistance of the welds. And as I mentioned, we're going to talk about physical issues and metallurgical issues. So some of these physical issues, for example, I went to a plant, a pulp and paper mill. They had sodium chloride solution in a pipe at 30 degrees C max. That's normally handled in 316L. We know that pitting and crevice corrosion can occur on 304L, or if the solution is overheated on 316L, but normally 316L is perfect. And the engineer who was not a weld engineer handed me this piece of pipe. It was actually the full 1 meter long pipe at this point, and said that there were holes in the pipe, and he blamed poor quality stainless steel. That he thought the weld was perfect because the weld did not corrode. But when we split the pipe in half, you could see that exactly what the problem was. The two pieces of pipe were butted up to each other. There was no gap there. The welder put a bead really on top of the two pieces of pipe. In the crevice corrosion started. And as I say, that particular environment, sodium chlorate, is known to cause crevice corrosion. However, because the weld bead was so thick, the path to the leak was through the pipe wall. So this is where the cause of the failure was welding and insufficient penetration. They did not have a full penetration weld. And as we know, and I've probably said many times, sorry, I'm getting rid of my something here, that the depth of penetration for stainless steel is less than it is for mild steel, and it's even lower for nickel alloys. But in this particular case, the welder should have allowed to have a gap between the two pieces of pipe. He probably should have tacked it, which he didn't do, at least on the root side, and welded it. Now, the welder would have known he wasn't getting full penetration, but he may not have known that the joint would fail prematurely because he didn't get full penetration. And so a lot of it is communication between the welding engineer and the welder. And another way of getting at it is if there was a visual inspection of the inside of the pipe or radiography had been specified, of course, that would have been clearly obvious. So in general, for corrosion services, we do want full penetration welds. And I would say, doesn't matter where it is, insist on full penetration welds. And in a similar matter, we don't want intermittent welds, because with intermittent welds, you also can get crevices created, and in many environments, crevice corrosion. Now, there are cases where intermittent welds are allowed or could be allowed, but you want to have it approved by the corrosion specialist who knows what exactly is in the solution and whether crevice corrosion is likely or not. So, and typical, and I've shown these slides before, that compared to carbon steel, the stainless steel needs to have a wider bevel angle, especially if you have thicker plate, a smaller root face, and a larger root gap. This was another case where, in this particular case, it was a start-stop defect that caused corrosion to occur. It didn't cause a leak in the pipe at this point, but eventually it would. And again, from the outside, the weld looks okay, although you might suspect that it might not have be the greatest, because it is so thick compared to the base material over the parent pipe there. And when you look on the inside too, you see all that heat tint, and I'll talk about heat tint in a moment, and that might raise a few concerns also, but only by looking at the inside of the pipe or radiography could you actually see the start-stop defect where corrosion started. Oops. And that's just a cross-section showing the amount of corrosion that has started there at the start-stop defect. Also, important always to look at the inside of pipe some way, and of course things like rough surfaces or pinholes are bad, and in most cases that is really a rejectable defect that should be repaired. And again, the welder actually knows what it looks like on the inside. He's seeing it. He's seeing whether he's getting gas evolution to get a pinhole or the rough surface because he perhaps hasn't purged it properly or whatever. But he really knows that. But does he know that this is bad for the intended corrosion service? And he might just say, well, I passed my bend test, I passed a tensile test, it's fine. Well, he hasn't looked at corrosion, and we don't expect him to look at whether corrosion can be an issue. So what about impairment of the passive oxide layer? And I'm going to go fairly quickly through these slides. You may have seen them elsewhere, but the natural oxide layer on a stainless steel is just a couple of angstroms thick, and you can see how many zeros there is in front of the one on the millimeter there. But visually, it's compared to a sheet of paper lying on top of a 30-story building. It can be made a little thicker by a chemical treatment, such as passivation, but it is very, very thin, and therefore it is subject to damage. Why is the passive layer important? Well, because it is enriched in chromium as an oxide compared to the parent material, the base material, and it's depleted in iron, so lower iron content. So it actually has, let's say, a higher corrosion resistance than the base material itself. So if it's scratched in air or in water, the chromium will pick up oxygen from either the air or even from the water and will quickly reform with an inverse exponential growth curve. It happens fairly quickly for the first hour or two. It might take 24 hours to get the final amount, but it's only a small incremental amount after the first couple of hours. Now, if the surface is contaminated with iron from fabrication during a fabrication process or in transport, the passive oxide layer will not properly form because it has iron on the surface. And this iron contamination only becomes visible when it is wetted and the iron actually rusts. Prior to that point, it's really in the metallic form, and it looks for the most part like stainless steel, but you might get a feeling that, okay, you see a scratch or something where there could be there. And so only when it is wetted and the iron rusts, you get iron oxide, and that is highly visible. The piece on the left there is from a forming operation. It got iron contamination from that. The one on the right is from a strapping material used to hold down pipe, and it was rubbing against the stainless steel pipe as it was being transported, left a mark on there, which wasn't visible again till it was left outdoors and in the humidity and started to rust. So there are corrosion consequences as well as aesthetic ones. And actually, I for most people, aesthetic can be as important as corrosion because you want your fabrication to look good. And so you don't want to send, if you're a fabricator, a piece of equipment that gets to the site of your customer and it has all sorts of rust marks on the stainless steel. He's going to raise questions about the quality of stainless steel that you used, or how good a fabricator you are. So heat tint, which you get from welding, is a thickening of the oxide layer on the surface. And as the heat tint gets thicker, it changes color. And instead of a protective oxide layer on the surface that has a high chromium oxide content, it will have a lower chromium content and thus a lower, in some cases, a very much lower corrosion resistance. And on the right, you can see some pictures. The one is of a weld. The one at the top is the heat tint was removed by picklings, no heat tint. Lighter heat tint, heavy heat tint, which is very bad. And then the very, very heavy heat tint is very, very, very bad. Now, in addition, as the chromium in the metal is oxidized during the welding process in the heat affected zone, there can be a chromium depleted layer of metal on the surface that is, again, lower in corrosion resistance than the bulk metal. It is not visible, this chromium depleted layer, because it is solid metal. And if you just remove the discoloration, you have not removed the chromium depleted layer. Now, in many cases, that may not be a huge issue, but in certain cases, it can be a very, very important issue, and you will have to remove also the chromium depleted layer. So this is a picture of a vessel, and it was welded, some structural side on the other side of it. So on this side, you're just getting the heat tint. And it's a bit strange, at least to me, although I've heard the explanations for it, that the That heat tint is the worst form of heat tint compared to heat tint right beside the weld itself. It has the lowest pitting resistance. Is heat tint always bad? Well, that's a good question. Well, let's talk about the formation of heat tint. So with gas tungsten arc welding or TIG welding, usually the torch gas is 100% argon, especially if you have a gas lens that the flow is not turbulent of the argon. You should only get a very light heat tint. The backing gas, most often 100% argon. Sometimes for critical applications, it can have a little bit of hydrogen in it. And that is perfect, but purging is really of a pipe is really, I call it a half art, half science, because getting it right, getting the oxygen content in the purge, what is behind the in a pipe is really tricky. It's time consuming and it's costly. Nitrogen can also be used as a backing gas. However, it has to be high purity nitrogen, and I've seen many cases where people just say, "Oh, we've got nitrogen," and they'll use something that's 99% nitrogen, but has 1% other gases in there, including oxygen. So it's important to use a higher purity nitrogen if you use that as a backing gas. With MIG welding, we normally say maximum 2% oxygen or sometimes 5% CO2 in the gases. That's okay for 304L, 316L. I wouldn't do that on the higher alloyed stainless steels, but they do give a darker heat tint than you get with gas tungsten arc welding. And many of the other processes don't protect the heat affected zone. And that is in some ways the most important area we're concerned about from a corrosion point of view, is the heat affected zone, the reduction there caused by heat tint. How much heat tint should be allowed? Well, that's always a good question. And of course, there's no easy answer to that. It's what we call the typical engineer's answer. It depends. Many years ago, we worked with AWS, the D18, to develop the D18.1 spec, and it was meant for the inside surface of sanitary tubing for food and pharmaceutical applications. They said you can't get, the number 1 level here perfect there. What heat tint is acceptable? They did different tests, and they said, well, up to this number 4 level, that is possible to obtain at a reasonable time period, reasonable cost. So 4 and under generally is acceptable in that application. 5 and above to 10 there is not acceptable. In other applications, you might accept a 5, for example, and this is assuming you don't do anything to remove that heat tint afterwards. Do I need to remove heat tint and surface iron contamination? Well, first of all, let's look at what kind of environments we should be concerned with. And generally, those are, to start with, environments where pitting can occur, and that's primarily where you have chlorides. Theoretically, if there are iodides or bromides present, that is also possible to get. And a pit will initiate in a weak area, for example, iron contamination or the heat tint, and it will continue to grow as the schematic on the right-hand side here shows that the chloride becomes enriched in the bottom of the pit, and it also has a lower pH. So the environment at the bottom of the pit is much more corrosive than the bulk environment in the solution there. And people say, well, what kind of ppm level of chloride should we be worried about? Well, we've seen it as low as maybe 10 or 20 parts per million, where if the chlorides can concentrate, usually through some sort of evaporation mechanism, that can cause the chlorides to rise to a much higher level. And so from a point of view of concern, you have to start thinking about it when you have 10, 20 parts per million. May not be a concern depending on the alloy until you get much higher, but you have to at least think about it and eliminate it if possible. Same can be said with crevice corrosion. Crevice corrosion is the same sort of mechanism, and that's why we talk about the issues of start-stop defects. You might have a crevice, intermittent welds, you might have a crevice, full penetration. If you don't have that, you will also have a crevice. And from an outside point of view, corrosion under insulation. So if that pipe that had the rusting from the strapping on it, you insulate it because let's say it was carrying some hot liquid or steam inside, that area will be the first one to suffer corrosion under insulation, that pipe there. Other environments are where contamination of the product is important. And certainly in the food and pharmaceutical industry, you don't want little bits of that oxide that is coming off floating around in your product. That would be a very bad thing. But it's not just those industries. There are certain chemicals which can be a problem. Hydrogen peroxide, for example, if you have the heat tint, it will deteriorate. It will break up into water and oxygen. So the heat tint, the iron will form as a catalyst. And I go back to the aesthetics. Most fabricators want their product to look good. Doesn't have to look perfect, but want it to look good. And if you have heavy heat tint such as this, okay, that's on the outside of the pipe. Maybe that won't have any effect on the outside in the particular environment that it's exposed in. But if I see that, it raises a red flag for me that how good is the inside weld surface? How much heat tint is there? Does this fabricator really know what they're doing if they allow this to occur? If that heat tint had been removed, you probably wouldn't have thought about it, but by just shipping it, and as I say, it may have no effect on the outside, but you certainly have concern for it on the inside. So what should we do about surface iron contamination? Let's take that at first. Well, first of all, you have to find it. As I mentioned, when it's just iron on the surface, it looks you can't really distinguish it from the stainless steel, so it has to rust. So you really have to find it first. I like the idea, if you can, and it doesn't work in all cases, of hosing down the piece of equipment, assuming it's all stainless steel, throwing a plastic sheet over it and letting it sit. If you know it's going to rain, you can just put it outside and let it sit in the heat and humidity and in the rain, but you really have to get that surface iron to show itself through rusting to actually see what it is. Now, some people will use wire brushing or a flapper wheel or a grinding wheel to remove it. It's partially effective. It certainly removes the rust part of it, but does not necessarily remove the iron contamination that might have not started to rust yet. Nitric acid, citric acid, they're used for passivation. They're not totally effective. They might, again, remove some of the iron contamination, but we have done it ourselves on some pieces of equipment that have heavy iron contamination, and they are not effective that way. So the more effective ways, there are some phosphoric acid cleaners that are pretty good. They might need repeated use. Ammoniated citric acid, again, that's one of those that removes light iron contamination better than pure citric acid, but doesn't remove the heavy iron contamination. And despite the fact that pickling, whether pickling liquids or pastes, are very hazardous. You need special equipment for the workers. They are really the best ones to use. They're nitric hydrofluoric acid-based chemicals. There's some newer, safer chemicals being tested now. A friend of mine is working on that now, just testing somebody's formulation. And we see that it works reasonably well on light iron contamination on 304, 316, but we're looking at it on other materials also, like the higher alloyed stainless steels. So what should we do? Well, about heat tint, well, you can actually remove the discoloration by wire brushing or a flapper wheel abrasive, but not necessarily the chromium depleted layer. A lot of people will glass bead or sandblast with a proper silica sand. It's more effective if done properly, not always easy to do around welds because you have a rough surface there. Grinding will remove the chromium depleted layer, but it's hard right to do at the fusion line unless you flatten out the entire weld bead itself on the exterior. And of course you want to, if you use a rough grinding wheel to start with, you want to smooth it afterwards. So it's because the surface roughness, the higher the surface roughness, the more likely it will pit also. And again, the nitric hydrofluoric acid mixtures are the most effective. And the pickling pastes are used for spot pickling. So if you just have a small amount of weld to do, you can just put on the pickling paste. You can also put it on the iron contamination areas too as pickling paste, and it works well. I see there are some questions. I'll have a quick look at some of them later, but if you want to put them into the Q&A, that would be great. But there will be a full time for questions later at the end. But I'll try to look after I get the physical issues. I'll try to have a look at some of the Q&A. There's just the typical before and after pictures for pickling. And again, this graph, and I've shown it many times, it talks about the comparative resistance to corrosion, specifically pitting resistance of the different surface treatments. With shot blasting, where you're actually, in this particular case, they actually blasted the material into the material. It wasn't a glass bead blasting. Brushing, grinding with the different roughnesses, and the 360 mesh, the finest grinding was the best. Pickling paste and pickling bath are both excellent ways of getting the optimum corrosion resistance from the material. Now, do we have to remove it? Well, I again go back to the aesthetics factor, and the picture on the left is a vessel. It looks beautiful, and the person who receives, whether it's a chemical plant, or in this particular case, it's a marine scrubber that's going on a boat, it looks perfect. The picture on the right shows rusty frames, and that sort of raises questions whether it's actually going to be a problem. That's another issue. It may not be a problem, but certainly if I were to receive it, I would certainly question the quality of the fabrication. And a certain amount of heat tint is generally acceptable. It doesn't cause a corrosion issue in almost all cases. So I'm just going to see, I'm going to look at some of the questions here. Okay, there was one on stress corrosion cracking. I'm going to address that very shortly here. Flux core welding is not allowed on stainless steel material. Yeah, some companies won't allow it, flux core welding on stainless steel. And part of it is that the flux cord wires from, let's say, 25 years ago were not necessarily the greatest. And there are some issues with lack of fusion there, but that's also true with some forms of MIG welding. I'm involved with MTI, Material Technology Institute, and we did a study on flux core arc welding in particular, and found that today the flux core materials generally are high enough quality and properly done. They are very suitable, and more chemical companies are allowing them. But still, there's some reluctance on the part of some welding engineers who had experience from maybe 25 years ago or more that they aren't good. Up to what temperature does the passive layer in stainless steel is stable? Well, it's stable until it starts growing through heat, and so reacting with oxygen in the atmosphere can cause it to grow and therefore reduce in corrosion resistance. I'd have to look at kind of the temperatures we're involved with, but it's probably close to 650, 700 Celsius anyhow. You get it growing so slowly that it doesn't affect the corrosion resistance. And how to remove the chromium depleted layer. Pickling will actually remove it. I actually did forget to mention that. If use the proper pickling liquids, and I say that most pickling liquids and pastes are designed for 304, 316 material. When you get into the higher molybdenum, the more corrosion resistant materials, the duplex materials, they will not be as effective, and sometimes you have to beef up the hydrofluoric acid content is usually what they do, or reduce the nitric content, and that will remove it, as well as grinding. But the pickling method is really the best way. And whether pickling or whether passivation is also required after pickling, that is the question that is very interesting, because there are people that will insist that once you pickle it, you need to passivate it. And the truth is that if you pickle it and the surface is clean, there's no oil and grease on it, so that the pickling action works. It removes all the contamination on the surface. It will passivate well in air. Now, if you do a chemical passivation through, let's say, nitric acid, it does increase the thickness of the oxide layer. It does make it more corrosion resistant, but I have to say more marginally corrosion resistant. And so it's not really needed in most cases. We were involved in an offshore project in Canada where it was seawater piping. They were using the 6% moly stainless steels, and their spec called for pickling and passivation, but the corrosion specialist with the offshore engineering company said, yeah, I know, if you pickle it properly, you don't need to passivate afterwards. So he wrote off. We didn't have to do the passivation on the welds after pickling. We just made sure that the pickling was done properly. Okay, I'm going to move on about metallurgical issues now. And what do I mean about them? Well, these are issues that are not visible to the welder, especially not visible to anybody. They occur on a microstructural level. They may affect corrosion resistance, and sometimes they can have a significant effect. And it includes not the weld itself, but the heat affected zone. This is especially where it comes in, because with the heat of welding, you're affecting the heat affected zone, sometimes detrimentally, not always, but sometimes. And it is dependent on the properties of the parent material. So it's not common to specify a corrosion test on the welding procedure qualifications or procedure qualification or welder qualifications. And so people have asked many times, should that be done? And of course, the answer is always, it depends. So I'm going to talk about just two types of stainless steel, the most common ones used for corrosion service, the austenitic and the duplex. So first of all, are weldments different metallurgically? And of course, the answer is yes. The weld metal has an as-cast structure versus the wrought structure of the parent material, which looks a lot different. It's been annealed. It's been worked so that the grains are completely different than the as-cast structure. And even if the even a cast material, if you buy a cast valve or pump, that pump has been annealed afterwards. So you do have a different structure when it's annealed. Not the same as the wrought material, but a different one than the as cast. There are high residual stresses in the weld metal. As the weld cools from a molten state, it actually shrinks and it pulls in the parent material in. You can get high stresses in the heat affected zone, as high as 100% of the yield strength. It actually can go above the yield strength and pull the material, and you can get very high residual stresses there. And this is where you have to be concerned about stress corrosion cracking and sulfide stress cracking. This is not something that the welding engineer should be left to decide. All welds will have high residual stresses. Yes, some might be a little higher than others, depending on your welding technique, your joint design, all that sort of stuff. But if the environment is going to have has a possibility for stress corrosion cracking, the one factor that you need high tensile stresses is going to be there. So I say this is up to the corrosion engineer to decide. Yes, if you have environment with high chlorides and even the temperature is up to we normally say it's most common above 40 degrees C, but it can actually happen as low as room temperature, ambient temperature, 22 degrees C. This is really something for the corrosion engineer to decide. And if he chooses 316L and he thinks that will resist the stress corrosion cracking, well, that's his call. But we know that 316L, when it has very high residual stresses, is very susceptible to chloride stress corrosion cracking. And you might question him about that. He may not know that. And it's really a whole separate discussion there, but certainly it's not up to the welding engineer to decide. Most austenitic alloys will have a 100% weld structure, will not have a 100% austenitic weld structure. We design the composition of the filler metals to have ferrite in there a little bit, generally a minimum of 4. In some cases, it can be as high as 20, but usually between 4 and 12, I would say, is most typical, where the austenitic wrought material is 99% plus austenitic phase. 304, it may have a little bit of ferrite in there. 316L, almost nothing. And you can tell with a magnet that sometimes if you have a plate, especially something thicker, that if you get a little bit of magnetic response, you have a little bit of ferrite there, but it's a very, very small amount. Whereas the weld will have, you want the ferrite there because the ferrite helps in preventing hot cracking. And one of my friends who's a welding engineer, he just said, well, welds, they have discontinuities on them, which he uses the word defects to mean something that is rejectable. Discontinuities just may be rejectable, but they may be just there and not have an effect. And we talk about tiny pores, inclusions, slag inclusions on the surface irregularities, all that sort of stuff that you don't get on the parent material. And of course, good welding prep helps and cleanliness helps. And I'll just say that most welders who start welding carbon steel, they have learned that, oh, there's a little bit of oil, grease, whatever, zinc on the surface. We'll just weld right over that. But they've always usually heard that they should remove it with stainless steels. It's very, very important that the weld joint be completely clean. So most of us in school or somewhere along the line have learned all about chromium carbide formation. Sensitization is another word for that, which affects intergranular corrosion primarily. Today, almost all wrought products are low carbon, less than 0.03% carbon. Few exceptions, bar, thin sheet, castings may not be. But plate products that are certified to 304 are most often dual certifiable as the L grade. And the exception, of course, is there is some plate that is certifiable as 304, 304H, H meaning that it has a minimum of 0.04% carbon. And 316L, if you wanted to find something that had more, 316, if you wanted to find something that had more than 0.03 carbon, good luck, because I won't say it doesn't exist, but you'll have to search long and hard all around the world to find it especially in a plate product, a thicker product, or a pipe product. Now, ASTM A480, which is the standard, one of the standards related to plate, sheet, and strip, it's done away with doing the test for intergranular corrosion. It just says it should be capable of meeting it. And the reason for that is that the standard intergranular corrosion tests they do, the copper sulfate test, it is so insensitive that it really is no value. When I worked at a bar mill, the only thing that failed it were material that we had not annealed. So if we had annealed it even poorly, it would pass. So it was a lousy test. It wasn't a sensitive test. So that's why they have eliminated it as being mandatory. Some mills will still do it. And I think even in Europe, they want it done, but it really doesn't tell you a lot. But certain applications, and I take the example, which is the most common one that I run across regularly, is for nitric acid service. When you're using 304L in nitric acid service, especially at the higher concentrations, like 65% and close to the boiling point, you can get it even in the L grade. And so they will specify the Huey test, the ASTM 262 practice C on the parent material, because they want to ensure that the parent material is fine. And if it can't pass that, there's no hope of doing a good weld on it. So this is really a check of the quality of the heat treatment of the material, and perhaps a check that there is relatively low sulfur and phosphorus contents that will meet it. So for weld metal, a lot of the same companies that want it on the parent material will ask it to be done on weld samples that you provide. And again, it's not going to be, for the most part, the weld that's going to fail. It's going to be the heat affected zone that is going to, if anything, suffer any corrosion. the picture shows, it's an old picture of a weld that is 304 that had relatively high carbon, 304L with low carbon, went through the Huey test. You can see the high carbon. You got that intergranular corrosion there. So let's talk about the standard austenitic alloys, 304, 304L, 316L. Are the matching filler metals suitable? And first of all, as a general rule, we want the weld metal to be at least as corrosion resistant as the parent material. Why is that? Well, the old galvanic or dissimilar metal effect, and if the weld metal, which is a small area, is less corrosion resistant and starts to corrode, well, the parent material does not. We have the bad situation of small anode, large cathode. So you have a galvanic, or at least potential for a galvanic effect there. If you have the weld is more corrosion resistant than the parent material, and the parent material starts to corrode, then we have the good situation of large anode, small cathode, and no galvanic effect. So we want the weld metal to be at least as corrosion resistant as the parent material. And so I'm showing here in the table the 304L plate at the top. It has 18 to 20% chromium. The filler metal, and I took the example of the wire here, it has a higher chromium content. So even if you lose some chromium across the arc, it oxidizes perhaps a bit, you will have a weld metal that is slightly higher in chromium content than the base metal. The nickel content is in the middle. It's less important from a corrosion point of view. And 316L plate versus 316L bare wire. Again, you can see the chromium content, which is the element most likely to be lost in a weld, is higher than the parent material. And so therefore, yes, the matching filler metals, they're not actually matching, they're slightly over alloyed. They are suitable in most cases. What about ferrite content? Well, as mentioned, those alloys, 308L, 316L, the composition of the filler metal is balanced to give some ferrite in the as deposited weld metal, and a small amount of ferrite prevents hot cracking, which can occur when that weld metal solidifies, especially as austenite. And in most cases, up to 10, even 12% ferrite is not detrimental to the corrosion performance of the alloy. But like all things in life, there are exceptions. And for example, in urea plants, there's a part of the plant that sees ammonium carbamate, and that is sensitive to ferrite, will cause the weld to corrode. At high temperature service, this is not necessarily corrosion. This is high temperature. The ferrite will embrittle, so it can cause embrittlement, which is a problem when you have a higher ferrite content, maybe 12, 14%. It reduces cryogenic toughness. The weld becomes slightly more brittle, not a huge amount, but it can affect that. And one should remember there are cases where ferrite is beneficial to corrosion resistance, and the most one that I run across is polythionic stress corrosion cracking, where ferrite will help to prevent that stress corrosion cracking from occurring, whereas the rock material that has 99% plus austenite in it will crack. So 304L, 316L, I call them forgiving alloys. So generally there's no issue. We mentioned perhaps with some cases like boiling 65% nitric acid, there is a problem. And the problem is more with the parent material than the weld material, but you usually test a weld because the heat affected zone will have a poor corrosion resistance, but generally, if the parent material is heat treated properly, is the right composition, it will not fail the test. And then there are some cases where we mentioned earlier where it is important. And now, can you use there are some cases where you may want to use a slightly higher corrosion-resistant filler metal for a particular service. It might especially be when you're doing repair welds. You might want to use on 316L a filler metal with 2.5% min moly rather than the 2.0, which you are almost guaranteed to get in the parent material. I've been involved in pulp and paper mills that will use 317L that has very similar to 316L, but has 1% more minimum molybdenum in it, or even the 309 LMO filler metal, which has a higher chromium, same moly content as 316L. Those are all suitable for welding 316L, where you're really concerned that you want the weld to be higher corrosion resistant. Often can you use 316L to weld 304L? And the answer is most of the time you can, but there are cases where 316L welds are less corrosion resistant than 308L welds. So it's nothing that should be done as a standard, but if there is a particular case, go and ask the corrosion engineer whether it is suitable or not. Let's move on to 6 moly stainless steels, and we're going to come up. I got about 10 minutes left here. 6% moly alloys require a very high annealing temperature, and this is where a lot of mills that make this alloy go wrong. To get rid of all the intermetallic phases that are present after hot rolling and that sort of thing, you have to anneal them at a very high temperature. And so we recommend that you do a corrosion test per heat treatment lot on the parent material, because if the parent material isn't good, the welder is only going to make it worse. There's nothing he can do about that. The 6 moly and higher moly stainless steels are most often used where resistance to chloride pitting, crevice corrosion, and even stress corrosion cracking are concerned. They're used in more severe environments. And so those defects that we talked about in the physical part are all extremely very important. Now, all these 6 moly stainless steels are welded with an overalloyed nickel-based filler metal of the 625 type or the C type, and there are variations on the C type. All of these have much higher molybdenum content and nickel content than the parent material. They have proven to be the proper ones to use for welding. However, sometimes there's a little problem with thinking about them. The 6% moly alloys are stainless steels, but they're being welded with a nickel-based filler metal. They have 0% ferrite in the weld, thus very sensitive to hot cracking. Thus, you have to keep the heat inputs down low. These are micro cracks that may not be obvious to the welder while he's welding it. They may only open up 24 hours after he's welded it. Now, we want low heat input, but we want fusion with the parent material and sufficient time to allow mixing, especially this is important on the root passes of pipe. With 6% moly alloys, autogenous welds, and that's welds without filler metal, are not permitted unless they are annealed afterwards. So basically, autogenous welds are forbidden, and this chart shows what the effect is, and on the vertical axis is the critical pitting temperature. The higher the number, the more pitting resistant it is. In the bottom is the horizontal axis is the molybdenum content. So with the solid line pointed to by the yellow arrow is the base material, the parent material, where the dotted line is the autogenous weld metal. And you can see with 316L, there's a small difference in pitting resistance, generally not huge, not a huge effect there. So generally you weld 316L in environments that may cause pitting, minor amounts of pitting with 316L filler metal. When you get into the 904L with 4% moly, you are seeing a difference, and therefore you shouldn't, if you know pitting is a distinct possibility, you shouldn't weld 904L with the matching filler metal or do an autogenous weld either. And when you get to the 6 moly alloys, there's a huge difference. So you should never weld 6 moly alloys without filler metal unless they're being annealed afterwards. Now, the real issue for welding is that if a welder is welding let's say a pipe and the joint, and he's adding filler metal to it, he knows it does, but the joint closes up as he goes around. And so he doesn't have to add filler metal, or he doesn't have to add much filler metal. He really knows he has to stop and open up the joint. You can't just have the filler metal in your hand. You got to be adding, and you got to be adding sufficient filler metal to it. So this is some training that the welder has to hear about, and it is possible to do weld tests. Often it is weld tests, the corrosion tests on welds. And it's important to show it to the welder. If you do an autogenous weld and you see how bad it is when you do it that way, that visual image may be more important. And some companies will specify the corrosion test on the weld procedure test, on the welder test to show the welder, and on production welds, just a standard one, just to make sure that people are following the procedure. And generally it's a 24-hour ferric chloride test. 40 degrees C is the temperature for most of the 6 moly alloys. I'm going to quickly move on to duplex, and they represent a whole new range of potential metallurgical issues. And there are some truisms I wanted to bring up here. Duplex alloys are the most cost-effective materials, and that's generally true. The cost of the parent materials are often lower if their high strength can be used, especially, but the fabrication costs generally are higher, and that message about the fabrication costs has to be put through to the people who are charging out this. You will need more tests, you have to do it different, and generally the fabrication costs are higher. Duplex alloy welding is not difficult, but is different, and I use that regularly myself. It does take a bit of a different mental approach to it, both for the welding engineer and for the welder himself. And when duplex alloys are good, they are very good, and when they are bad, they are very bad. And that is a truism I also use regularly, and a good example of that, and I thought I had a picture here, well, we'll come back to that, but because it is in the next couple of slides, I have an example of where that is the case. So with duplex alloys, again, the proper heat treatment of the parent material is extremely important. If it's poorly heat treated, it may not be possible to weld it in good corrosion resistance in the weldment, in both the heat affected zone and the weld metal itself. And so therefore you need to do tests, and that's limit shown in ASTM A923 for the duplex rates 2304 and higher, or one for the lean duplexes A1084. And that ensures that there's freedom of intermetallic phases in the parent material. And in the oil and gas industry, they use the ISO 17781 specification, which is an excellent publication. And if you're doing a lot of duplex welding, I would recommend buying that, because it covers a lot of really good things there. So if the parent material is poor quality, there's nothing the welder can do to make it a good quality weld. So austenite ferrite balance, corrosion issues. There are tremendous corrosion issues if you end up with too high ferrite, as well as poor toughness. It becomes brittle at low temperature. This is the most common problem. We can do a whole webinar on duplex welding. I think I've actually done one for IIW, but it needs to be controlled by many factors. Minimum heat input, which is completely different than austenitics. No minimum heat input for austenitics. There is for duplex alloys. The thickness of the material, the particular duplex alloy, the filler metal being used, the welding gas, many other factors. And so this is a microstructure of the black is ferrite. You can see this has very high ferrite content. We really want it to be 50-50 or close to that, maybe 65 max. This is a fire that's happened at a refinery because one weld in duplex cracked, sulfide stress cracking. It was a weld where they were welding thin material to thick material, and they didn't do any special welding tests on it, both either as a qualification test or as a production weld, and it cracked, caused a fire, millions of dollars in damages. There have been other fires at other refineries that have had the same issue, and people have been severely injured and even have been killed. So when duplex is good, it's very good. When it's bad, it can be very, very bad. So I'd like to show this, and I'll go through it very quickly about what happens, why it's important. If we have on the vertical axis is the temperature, you can ignore the composition. We've chosen a duplex composition here, and this blue arrow is as it goes from liquid through to solid and then all the way down through temperature. Up at the top, it's 100% liquid metal, and then we have liquid and solid forming. I call it slush. Those of you who know snow, you have been in slushy conditions. And then it becomes 100% solid. And when it becomes 100% solid, it is 100% ferrite phase. And if it is cooling down slow enough, some of that ferrite starts to transform to austenite. And once you get to about 1,000 degrees C, if you've done it slow enough, you will have a structure close to the 50-50 austenite ferrite range that you want. Nitrogen aids in the speed of the transformation, which is why the nitrogen is extremely important in the duplex alloy. Nickel also does that. But once you get below 1,000 degrees C, if you have too slow a cool, it's you can get intermetallic phases that form, and this is one of those things that is very difficult for welders to understand. So it's really something the welding engineer has to get through in his own head. And up here is the temperature range where these detrimental intermetallic phases can form, and they form much quicker than with austenitic alloys in duplex alloys. They can form in the heat affected zone. They result impaired corrosion resistance as well as impaired mechanical properties. The micrograph on the right just shows there's some small dots there of intermetallic phase that has formed there. So what are important in the welding? Well, loss of nitrogen from the molten welding pool. Nitrogen can come off, so you have it in the base material, goes into molten state, and some nitrogen can come off, and that can result in lower corrosion resistance and a poor phase balance. Like the SigmaWeld alloys, we generally say no autogenous welds. They may be under special circumstances, and unlike the 6% moly alloys, austenitic alloys, the reason is more the phase balance issue, not the intermetallic issue. There's a limited number of filler metals, and I'll come a bit more into that right now. Up in the top, we see two versions of 2205, the UNS S31803 alloy was the one that came first through. I was around, I'm an old guy. It came through in about 1980, and the composition was the normal range for chromium, nickel, molybdenum, and nitrogen for that time. But it was quickly realized that if you made the composition to the bottom end of this range, it really was a completely different alloy that had major problems in fabrication than if you had something in the middle range of the chromium, molybdenum, and nitrogen content. So that's where the S32205 comes in. It has higher minimum content, same maximum content, so they really fit into the same specifications. And really, most importantly, it's the nitrogen content is in the high end, because we said nitrogen aids in the transformation of ferrite to austenite as the weld metal cools. Now, one of the issues is that for the filler metals, the chromium content is just slightly higher than the original base material, but it can be lower than the modified version. The molybdenum content is still at the minimum level, and the nitrogen is at again the minimum level. And this can create a problem if you're welding the S32205 alloy if you haven't checked to make sure that the filler metal you're using does have a higher chromium and molybdenum and especially nitrogen content. Now, you'll see, first of all, that the filler metals are all elevated in nickel, and that is also because nickel is easy to add and will help in that transformation. And so it works in many cases, but not all cases. And when it comes to bare wire, there are a number of producers that don't like the 0.14 minimum nitrogen content, and they need a, it makes it very difficult to produce for them, higher defect in the wire production, and so therefore they resist it. So many times you can get away if it's 0.13, 0.12% nitrogen, but there are cases you may want to insist on the 0.14 minimum nitrogen in the bare wire. So testing requirements, there are a whole raft, there are many specifications. ISO specification talks about that for the welds. They should be specific to the application, to the alloy, to the thickness and welding processes. With many of the duplex alloys, corrosion testing as well as phase balance tests are necessary at many stages of qualification to make sure you have it right. I'm not going into all the details there, but basically there are so many cases where you need it. Test with the actual filler metal to be used on duplex weld products, and test additional and unusual configurations. And the most obvious one is when you're welding thick plate to thin plate, you can't have too high a heat input there or you'll burn through on the thin plate. You have to be very, very careful there. So just in summary now, not every imperfection needs to be corrected, but it is important to know which ones are going to affect the corrosion performance, and that should be shared by the welding engineer with the welder so that he knows what is important. He often knows much better as he's welding it what is happening there. If he knows that it's bad, he might do something about it. And the heavy heat tint we've talked about, sign of something going wrong, and certainly raises a big red flag for me. With the standard alloys and the metallurgical issues, really there isn't a lot. Just we talked about nitric acid. We talked about a few cases where ferrite content may have an effect. And when I come to repair welds, you as a welding engineer may have to assess the conditions to see whether you want to use that matching filler metal or perhaps a slightly over alloyed filler metal. With the Sigma alloys, it's really up to the welding engineer to ensure that a proper specification exists and it is followed. Maximum heat input, proper filler metals, no autogenous welds. Heat tint should be removed, preferably by pickling, because it gets the chromium depleted zone. Corrosion tests on wrongly welded material can illustrate to the welding foreman and welders of the corrosion consequences. I've done that before. I've showed them a sample of an autogenous weld with huge pits in it from the test, and they are shocked in some ways and say, okay, I better not do it, even if it may take 6 months for it actually to show up in practice. And with the duplex alloys, yeah, it's a lot more difficult. I'm a big fan of duplex, don't get me wrong. They are wonderful alloys, but you as a welding engineer, you really have to take a much closer look at them. It's going to cost more to do the testing. You need to do special things that you aren't doing with the austenitic alloys. They are different, but not necessarily difficult. So much of the data I have presented is available on our website in the library, www.nickelinstitute.com library. Please join us on LinkedIn, and we offer free technical help from our worldwide consultants. And if you go to the address at the bottom here, inquiries.nickelinstitute.org, it will ask you to set up an account, but that's just so that we can ensure that we're sending it back to you, the answers. Then you can enter your question, and for the most part, you will get an answer within 48 hours. And with that, I will look for questions.
Thank you so much, Gary.
Yeah.
As usual, very concise and detailed presentation on this, and we have about 22 questions going in the Q&A section below. Would you like to take some of them?
Yeah,
now?
sure.
All right.
I'm just looking at them now here.
First one is, will we have the confirmation on the contact hours after the seminar which help on CPD records? I think as Gary shared the link, you can email them there in case you have anything that you need regarding the presentation. Yeah.
Okay. I'll send the PDF of the presentation to you, but do you offer? Go ahead.
We can share it out on the email list that has come in. So if required, we'll share it out, right?
Yeah.
And there's a question from Gerald which says, how does an welding engineer ensure SCC testing?
Okay, so I've done the first the questions up to that in at halftime there. So I'm down to that anonymous attendee. What if stainless steel equipment to be abrasive blast cleaned and painted, or thermal spray coated after welding? Do we have to pickle the weld to remove the heat tint? So if you're doing an abrasive blast, you can make sure that will remove the heat tint. If you're painting it, you're obviously covering up the that area. So no, it's not necessary to get a thermal spray. I guess it depends on what kind of thermal spray it is, whether you need to do that. But I would say in general, unless it's a very heavy heat tint, I wouldn't remove the heat tint there. The question about the best method to measure the level of heat tint inside a pipe weld, the root side, and that is best done visually by looking inside there. Of course, that's a real skill to to put in your scope and have a look at it. And it's not optimal, but but it is really the best way to have a look at it, and then use that chart that I showed that to give you an idea of how heavy it is in there. And while you're doing it with the borescope, you're also looking for any defects, whatever start-stop defects, porosity, lack of penetration there. So it's really best done by a borescope there. If you can't get in it, well, it's just to make sure that the welder has purged it properly, that he's left enough time for that, for all the oxygen to get out. But excuse me, but yeah, it's you really, it is a hard time. And once, if you have too heavy heat input, you can remove it by flushing pickling solution through the pipe system. Let's say that's very expensive, very costly. So it really is best to try to avoid it in the first place. What would be the minimum oxygen content in ppm to ensure discoloration level 4 or less? I'd have to go back. I believe it was 20 parts per million oxygen, but it may have been slightly lower than that. Certainly,
I think
most
for
people
titanium, they go as low as 10 or 2.
Yeah, titanium is
And for-
extremely important.
But stainless steel, I think 20 is good.
Yeah, okay, thank you. Are there any other than?
Graham has also commented on this, that AWS has 40 ppm O2, but color SS.
Oh, okay. Yeah.
Thanks, Graham.
Yeah, and it really depends on. I was involved in a project in the mining industry where they were using, they were welding 904L pipe, but the solution that was going through it would really pickle or take away the heat tint, and there was no chloride in it of any consequence. So they really, even though they did have heat tint on the inside at a higher level than 4, they really didn't need to do anything, because the service that they were putting it in, it would actually take away the heat tint, and because it was mining industry, they didn't care about any contamination that was showing up. There's a question about and it's actually A480. Well, the practices are actually in A262, but A480 references the intergranular. If you use a low carbon, you really should not be concerned about intergranular corrosion, except in very severe oxidizing environments such as nitric acid or perhaps chromic acid. So it really doesn't need those tests on it. There might be some where some of the other practices are possible, but it really, I mean, people concentrate a lot on those practices, but in a low carbon grade, I really don't think they're necessary if you buy from a reputable mill. Yeah, pickling and passivation. So pickling is generally a nitric hydrofluoric acid mixture. Passivation is strictly nitric acid or perhaps citric acid. They are completely different methods. Pickling literally dissolves some of the stainless steel. That's why it will remove some of the chromium depleted zone, which is a solid, it's not an oxide, it's a solid metal there. Passivation doesn't dissolve any of the metal. Is pickling paste with 20? I'm not sure what 20 to 25 T is, but maybe that is percent. It's always a balance. The hydrofluoric acid content in, the question is pickling paste with 20 to 25, and I'll assume it's percent concentration of nitric acid and 5 to 7 hydrofluoric acceptable for 316L. It's always a balance between the nitric acid and hydrofluoric. And if you 5 to 7 hydrofluoric is very high, but if you have a high enough concentration of nitric, that will prevent a lot of general corrosion. You would really I'd have to look to see what it is, but the 5 to 7 sounds very high in hydrofluoric acid content. As cast structure of weld metal, is it always considered anodic or less corrosion resistant? Well, that's a good question. In many cases, like you can have a difference in galvanic potential between the two, and it can mean nothing in actual practice. So perhaps because of the high stresses in a weld, the different structure, in most environments, it probably is considered anodic per se. If it were identical composition, is it anodic because you have a slightly higher composition? In the end, I'll just say you want it to be more equal to or more corrosion resistant, and therefore, in most cases, it's not a problem. But there are cases that the high stresses that are in a weld will cause it to be anodic there. Oh, A262, A, B, C, or D. I'd have to, yeah, I mean, because there's a different structure in the weld behaves differently in these tests. Then the parent material, and just as an example with the practice C, which is the nitric acid test, because of the structure of the grains in a weld, you rarely see a lot of intergranular corrosion. You might see more general corrosion in the weld, where intergranular corrosion is common in the heat affected zone because the carbides can form at the grain boundaries. And if there's a continuous line of carbides, of course, it will be attacked rapidly and would fail the test. What happens if the silicon content of 316L has been 4%? Okay. I think actually this question, what happens if the silicon content of the 316L stainless steel has to be is 4%, and if other elements are within tolerance as per the material standard? And I believe this question was asked on our technical service line. I think I saw it, and I think if you measured it at 4% by a PMI unit, I would recalibrate the PMI unit, because no 316L should have 4% silicon unless it is being used for a very specific example, and it's usually 304L, not 316L, and that's for high temperature concentrated sulfuric or high concentration nitric. So my first guess is that it isn't 4% silicon, because those grades with 4% silicon are very difficult to produce. Silicon helps to form intermetallic phases, so I would suggest first that the PMI result is wrong. Low ferrite welds with ER316L with manganese generates porosity issues due to probable nitrogen in it. Any suggestion to overcome the same? Sub-arc welding is being used. Well, sub-arc welding is, first of all, a very high heat input process. And if you have low ferrite, you're apt to get hot cracking. So you have to run it, first of all, very low. I've just never really run into porosity other than perhaps because of moisture that's in the weld joint or other contaminations. So I would, the 316L with high manganese, which gives low ferrite, it shouldn't have, maybe it does have high nitrogen in it. I'm not familiar with that particular one. I would look at it. It shouldn't have high, it's a bare wire, so I'm guessing it won't have high nitrogen in it, but if it does, that is certainly a possibility. But if you want low ferrite, I would try to get a wire that without high manganese content, that because they would generally have relatively low nitrogen in them. When is 304L filler metal superior to 316L? Oh, well, it is in highly oxidizing environments. Nitric acid is the most common one, and so it is generally wanted to be used in, and this is only in high concentration, 65% high temperature surfaces. Which stainless steel material is good for chloride stress corrosion cracking? Well, the question is how severe is the chloride stress corrosion cracking risk? And that depends on the pH of the solution, and there's an if it's a high enough pH, you don't need even 316L may work perfectly fine. If it's in an intermediate pH range, you may need to go to a duplex, and then if it's lower, then you might have to go to super duplex, or you may have to go to a nickel alloy. So it's very, very complicated, and I have done corrosion seminars on chloride stress corrosion cracking, and we it's a very complex issue. So it's not an easy answer. Why 0% ferrite alloy require low heat input? This is related to the filler metal, but also the it's hot cracking. So things like sulfur, and especially sulfur, but other contaminants can do the same. When you weld, these contaminants often are the ones that are last to solidify in the weld pool, and you end up with high concentrations at grain boundaries, and that causes cracking to occur because you have a lot of stresses there. It tends to pull them apart. Any specific recommendations to enhance corrosion resistant properties during solution annealing? Well, solution annealing or heat treatment after welding, in the end, you really don't want to do that unless you have to. And why is that? Well, at least in a piece of equipment, because the heat treatment temperatures are maybe 1025 degrees C, 1050 degrees C, you're going to get distortion. You want to cool it quickly afterwards. Where it has to be done, you have to do it very, very carefully, and duplex alloys especially are tricky to heat treat, because even though they're stronger than, let's say, the austenitic material at room temperature, maybe up to, I don't know, 600 C or whatever, once you get to the very much higher temperatures, the annealing temperatures, they're a lot softer. So they need special support so they don't flatten out or distort when at the annealing temperature, but then you want them to cool quickly, and so often the distortion comes when you try to do a fast, even a forced air cooling, which is only possible on somewhat thinner material. So nah, don't have any. My recommendation is don't do heat treatment after welding unless you absolutely have to. Do we have time for more questions?
I think we can take one more, Gary, and then we can conclude.
Yeah, we can try to answer these after by email.
By email. Yes,
yeah.
sure.
So when welding high thickness duplex welds, how to ensure required ferrite austenite balance in the middle layers? Well, that is a good question in terms of, yes, you are concerned about that. If you get it right when you're actually doing those passes, you will never end up with a higher ferrite content when you weld on top of it. The heat treatment caused by the additional passes will only help to increase the austenite part. However, we are concerned about the intermetallic phases that could develop because of all the extra heat in that temperature range, which is roughly, I always have to think in Celsius here, up to certain grades up to 1,000 degrees C, and probably for probably 550 degrees C to 1,000, let's say. You may have intermetallic phases forming. Will that be a problem? Well, you have to prove it, but the key is to make sure that it's the proper austenite ferrite in the weld pass that you have laid down. And of course, that's part of the welding procedure. When you slice it up afterwards, you can do that. Some people will actually take a ferrite scope and measure the ferrite content, but it's really hard. The ferrite scope only measures, it has to be a roughly smooth, flat surface as best as possible to get an accurate value, and they are tricky to use. I prefer doing the metallographic examination, and it can be done at the end too to see how it is after all the passes are done on the procedure qualification welds. Okay, I'll leave it at that.
Thanks, Gary. I think one last question, if we can take for Adi. Adi Sukardi has joined us from Indonesia Institute of Welding, and he was a speaker here. I think his question is, why autogen not recommended for duplex if we can control nitrogen and oxygen content?
Oh, okay. Yeah, so there's been a lot of work going on adding nitrogen to the TIG shielding gases, and some people will add 2% nitrogen to it. And it, first of all, I'm not an expert on this in terms of a lot of experience on it, but I have seen cases where sometimes too much nitrogen goes into the weld, and you get nitrides forming, but that doesn't happen all the time. So I think it has to do with the flow of the gas. Of course, it has to be a high purity nitrogen that's put in there. But yeah, it is possible to add nitrogen to it. It deteriorates the TIG, the tungsten. So you have a sharp point on the tungsten, and it causes it to be a bit rounder. So you got to sharpen the tungsten more often, and that's usually the thing that people complain about most when they try to use the purge or with the shielding gases with nitrogen in it. if it works for you, if it gives good results, you're happy with it, I would say there's no reason for not doing it, but there can be issues, and you might want to check to make sure you aren't getting nitrides. And it depends a little bit on the duplex alloy also, I think too. So yeah.
All right. Thanks so much for answering all those questions, Gary. And the rest of them, maybe we'll share it with you via email and take it up later. Abhishek, would you like to say the word of thanks, please?
Yeah, sure. Thank you, Nimesh bhai. Yeah, hello once again to one and all present here. I'm Abhishek Vyas, Honorary Secretary of the IIW Mumbai branch. And it is indeed a great opportunity for me to express my gratitude and thanks to our speaker for today's session, Mr. Gary Coates, for a very informative session on how can I know if my stainless steel weld is sufficiently corrosion resistant. Thanks, Gary, for covering most practical aspects, including discussion on the heat taints, metallurgical problems amongst the various stainless steels family, and yeah, the remedial actions for the same. I would also like to extend my thanks to Mr. Hugh Schweizer and Mr. Graham Sussex for being with us today for this webinar as the panelist. We at IIW Mumbai branch are also thankful to Mr. Nimesh Chinoy and SigmaWeld team for sponsoring this Weld Tech Talk series. Thanks also goes to Dr. Krishnan Sivaraman, who is not there today, and the core technical team of IIW Mumbai branch, who are behind organizing these excellent Weld Tech Talk series. We are also thankful to the big number of participants that attend our Weld Tech Talk series continuously and for asking the most relevant queries to the speaker, which helps us, all of us, to increase our know-how on the subject. Thank you everyone once again for making yet another Weld Tech Talk from IIW Mumbai branch a great success. Thank you everyone. Stay tuned with us for further series.
Thank you, and see you in Delhi at the Indian Stainless Steel Expo.
Sure, George. I'll meet you there on Monday. On the 3rd. On the 3rd.
Yes,
all right.
absolutely.
See you.
Thanks. Bye.
Bye-bye. See you.
Bye-bye.
Thanks, Gary. Thanks, everybody. Bye-bye.
Yeah,
thank you.
Bye-bye.